Okay, so today we're going to take a look at how the formulas in the formula sheet, your blue book, can be used to help you with the details of z-scores and confidence intervals and hypothesis tests. So we've not really looked at this yet, and it's time to do it now. So if you pull out your blue book, if you have your book with you, pull out your formula book. If you don't have it, just watch and find your book and bring it with you. You need to start using this because it's your go-to tool on exam day. Okay, so if I go to the first page, these are formulas for AP Statistics, and what we need for inference for all the decision-making business starts at the bottom of the page. So we go all the way down to the bottom of the page, and I'm going to just fold this so that it's not quite so hard to pull with. At the bottom of the page is where the sampling, distribution, and inference starts. So we have the very first thing here is called the standardized test statistic. Now that is fancy wording for at this point in time for us, it's a z-score. So let's think about what we know about a z-score. Z is the observed statistic that we saw in a sample, minus what we expected to see. This is the language we've been using, so that's the parameter from the model, that's usually the mean of your normal curve, over the standard error or standard deviation. So most of the time in inference we use standard error because we're basing it on a sample instead of on an actual known parameter. So this is what we've been doing all this time. So observed minus expected over standard deviation. So I'll say standard deviation. That's the language we've been using. So now that we've been in inference world, when we do hypothesis testing and we get into the mechanics and we need a z-score to see where our sample lands with respect to what we proposed in our null hypothesis, we've been saying z is equal to the p-hat, the observed proportion from the sample, minus the true p that we're assuming in our null hypothesis, what that claim that's made, that status quo, nothing has changed claim about the population parameter, no hat, over the standard error or standard deviation, depending on what we know. So that's some sort of a formula. For us, it was the square root of p times q over n. If it's a hypothesis test, we claim to know p, so that's the p that was claimed in the null hypothesis, as opposed to the p-hat from the sample. So this is the structure of the z-score we've been using. So this is the same thing as this standardized test statistic. But it's generalized in the blue book because there's more than one type of test statistic. A z-score is just the first one that we learn. When we get into quantitative data analysis, we will move to a different model called a t-model, and then we'll change this to a t-score. So this is generic because we use it for more than one type of test statistic. So we find a z-score when we do testing because we want to know where in our normal model, if we're assuming some p from, if we're assuming some p for the population, and there's some sample p-hat that has been seen in a sample, an observed sample, the z-score tells us how many standard deviations from the mean we are. So it gives us a test statistic, or a place to kind of a statistic with which to run the test. And so then you see some generalized terminology on the other side. So the statistic is the sample statistic. Statistics always come from a sample. So that's the general word for this p-hat. The parameter is the truth that we're defining for our model. The parameter is always about some property of the model. So that's the p from the model. So that's always p without a hat. And then the standard error, this is the standard deviation formula that we've learned. Now, the standard deviation formulas are in this book. If you look on page 2, we've looked at it before, so we're going to pull it back out. If you look at the second page, at the top of the second page, you have random variables, parameters of the sampling distribution, so that's the mean and standard deviation, and then standard error of the sample statistic. So notice that these two formulas are the same, other than this one has hats. So when you put hats on your p's, you get a standard error, which is S instead of sigma, and that's used in the confidence interval calculations. And then the sigma p hat is used for hypothesis testing. So technically you really are doing standard deviation when you're doing hypothesis testing. They're the same formula though. So you come over to this page and you pull out your standard deviation or your standard error formula, and then you stick it into the general formula for a z-score that's on the second page. So all the pieces that you need are in your formula sheets, but they have to be pieced together because your formulas are somewhat general. The easiest thing, of course, is just to know your z-score formula off the top of your head. Z-score is something you use all the time. It's one you should just know. But if you need a standard error formula, then you come over to page 2 and you dig out what you need. Okay. The second thing we need to look at is the confidence interval. So that's in the second box. Confidence interval, the general structure is given here. And again, it's generalized because we won't just do one type of confidence interval. We're going to learn to do several types of confidence intervals. So the confidence interval that we learned in the last chapter, actually in this unit, was the 1 proportion z interval. For the 1 proportion z interval, our statistic was the p hat that we got from the sample. That's the point estimator, plus or minus. So what comes after that is the margin. So you add something to the middle, you subtract something from the middle, and you get a margin. You get an interval itself. Then comes the critical value, which is the terminology for the z-star. When we move to to quantitative data, that's going to change to a t-star instead of z-star. So that adjustment will come later, but that's why this is generalized, because there's more than one type of model, there's more than one type of critical value. For now, z is all we know. And then multiply that by the standard error of the statistic, which is the formula from over here on page 2, that one right there. So square root of p hat q hat over n. So this is the confidence interval formula that we learned in chapter 18. And so this is the one that it would just be really handy if you knew off the top of your head. But if you couldn't remember what pieces go where, this is your formula in general terms. Statistic, put in a p hat. Critical value, z-star. Standard error, formulas in the book. Okay, so we're going to learn, starting tomorrow, how to work with 2 proportions. So instead of just worrying about 1 proportion and how it relates to a claim made for the population, we will compare 2 things. So if we want to compare the percentage of men who have a high school diploma versus the percentage of women who have high school diplomas, and we want to see if they're different, then we would compare 2 proportions, and that's a different type of inferential procedure. So that's what we're going to dig into tomorrow. And the only thing that changes when you start looking at 2 p hats and 2 p's instead of 1 is that in your standardized test statistic, your z-score, your statistic is actually the difference in 2 p hats, and your parameter is the difference between 2 p's from the population. And the standard error formula has to grow into the standard error formula for 2 proportions. And that handy dandy formula just so happens to be in the formula book. So you'll notice right under, for 1 population, p hat is your random variable, that's your statistic. The mean of the parameters, mean and standard deviation of your sampling distribution, your normal model, are here. with the standard error, and then you have matching things right under it for two populations. So if I wanted to compare two percentages from two separate populations, then my sample statistics difference would be p hat number 1 minus p hat number 2, which might be p hat for females minus p hat for males. We may use subscripts that help us keep up with what our populations are. When we find the mean of the model, it's going to be the difference in the true proportions. And then when we find the standard deviation, we're going to use this big ugly formula, which is basically a Pythagorean theorem application on this. When we did random variables back in chapter 15, we learned that the difference of two random variables had a standard deviation of the square of the first standard deviation plus the square of the second standard deviation, and then take the square root. It's a Pythagorean relationship. So this actually piggybacks off what we learned in our random variable rules back when we were combining dogs and bones and dogs and chomps when we did the Detmer dogs activity. So this is a spin-off from those formulas we learned back in that chapter. You don't have to memorize the formulas. They're right here. You pull them out and you stick them into your mechanics as you need them. So we're going to dig into pulling these more sophisticated formulas out of this blue book and using them to do two proportions starting tomorrow. There is a special case that we'll look at on Wednesday where sometimes you have a different formula that has to be used. Technically, we're going to use this formula right here for confidence intervals and this formula for hypothesis testing. So it gets kind of messy. There's a lot of stuff going to be going on, and it's a lot of stuff to memorize. So it's our best bet to learn how to look up in our blue books, look up in our formula sheets what formulas we need when we need them, and put them in the structure of what we're trying to compute, whether it be a confidence interval or a z-score for the mechanics of a hypothesis test. And we just have to learn how to put those pieces together to do the work that we need to do. So that's it for today, is just to take a look at these in the blue book so that we kind of know what's coming, know where to find them, and then there's a little bit of reading that you are to do before tomorrow just to kind of get your feet wet thinking about what two proportions look like, and we will dig into notes over confidence intervals for two proportions tomorrow.